Hello and welcome. I am Verdugo, and today we are going to talk about partition arrays, which is a new Julia package for sparse linear algebra on HPC platforms. This is a collaborative work between Alberto Martin from Monash University and myself from Free University Amsterdam. So what is partitioned arrays? In short, this library provides two main types, p-vector and p-sparse matrix, which are vectors and matrices that can be used on distributed memory machines. You can see in the picture that we adopt data distribution based on row splitting, so each processor will store only a subset of the rows of those matrices and vectors. And apart of that, the library also provides its own parallel execution model to help developing parallel code in Julia, as we are going to see in a second. We decided to start this library since we are interested in the solution of partial differential equations using numerical techniques. In particular, I am one of the main developers of GridUp, which is a finite element library implemented in Julia. And as you know, when you solve PDEs with finite elements, you end up having large and sparse systems of linear equations that for complex problems need to be solved in parallel using supercomputers. To do so, you have several options. For instance, you can use PETSc, also from Julia, by using PETSc.jl, but this approach was not convenient for us because PETSc forces you to use MPI, which means that you cannot use Revise and other tools to develop your code. And this is because MPI forces you to launch your code from the terminal with commands like this one, which means that for each run you're going to start a new Julia session and compile all your code, which can be very time consuming for complex examples that like these ones that may take up to several minutes to compile. So it was clear that this was a bottleneck in our workflow, and we decided to look for a solution to this problem. And we ended up having a framework that allows you to use MPI for production runs, because we still want to use MPI for production for performance reasons. But at the same time, this framework allows you to use the standard Julia workflow for the development. Okay, and this is done by using two backends. So you can develop your code in a sequential Julia session by using a sequential backend. And once everything is working properly, you can switch to the MPI backend and deploy your computation on a supercomputer. Now, to illustrate the workings of these two backends, I have prepared a very simple example in which we say hello from each one of the MPI ranks. And as you can see, you can develop this code in this notebook by using the sequential backend. So this is not running in parallel. Actually, this is running with a standard sequential loop over these three parts. But once everything is working, you can switch to the MPI backend by changing a couple of lines in your code, and then you end up having an MPI application that can be deployed on a supercomputer by using the standard MPI commands. Now, in this second example, I want to show you how to solve algebraic systems with this library. And to do so, I'm going to solve this finite difference system in parallel by using three MPI ranks. And the code to solve this system is as follows. So first of all, you have to choose the backend. In that case, we are going to use the sequential backend for demonstration purposes. Then we choose the number of parts in which we want to split our data. In that case, we use 3 parts. And then a very important step is to get the part IDs with this function. And then you end up having an object, a distributed object, that for each part contains its own part ID. As you can see in the picture, for the sequential backend, all these values will be stored in a standard Julia vector, but for the MPI backend, this object will be actually a distributed object, and each MPI rank will receive only its own part ID. Starting with this distributed object that contains the part IDs, you can transform these quantities to create more sophisticated data. For instance, to create the local values of the right-hand side vector. And this is done by mapping the part IDs, you can see here. So here it's interesting to see that for the first and last parts, we need to include boundary conditions in the local values, but not for the other parts. And again, in the picture, you can see that for the sequential backend, you end up having a vector of vectors, but for the MPI backend, you will have for each MPI rank, so each MPI rank will contain only its own local values. The second ingredient to build the right-hand side vector is to define the row partition. This is trivial in that case because this is a one-dimensional uniform partition that can be created with this function. And finally, once we have the values, the local values, and the row partition, we can create our right-hand side vector with this command. For the matrix, this is more or less the same, but now the local values will be sparse matrices, of course. And here the tricky part is the column partition, because each part will get the non-zero columns associated with their own rows, and in that case this will lead to some overlap between the parts. But again, in the library we can create also this type of column partition using inbuilt tools, in that case by using ghost values with this command. Okay, now we have the row and column partition and also the local values, and we can create our system matrix with this command. Now we have a matrix and a vector, so let's solve the linear system. For this particular formulation, the initial guess of the iterative solver needs to fulfill boundary conditions, so we can create an initial guess that fulfills boundary conditions as in a similar way as we have constructed the right-hand side vector. And now we are ready to solve the linear system, for instance with a conjugate gradient method from the iterative solver package. So note that all the functions that iterative solvers is using have been overloaded with parallel methods. So when you deploy this code with the MPI backend, you are going to solve this system in parallel. And finally, to show that you can use some linear algebra on this object and compute the residual and also the norm of the residual to check that everything has been computed correctly. And again, all these methods have been overloaded with parallel methods for the MPI backend. Just to finish, I want to show some performance results. In that case, for a 3D Poisson problem, and here I'm showing the wall time spent in the finite element assembly of the system, and as you can see that we get a nice both strong and weak scaling up to tens of thousands of CPU cores, which shows that with this library you can really solve also large problems, not only academic examples like the ones showed in this notebook. Okay, just to finish, I want to mention that this package is under active development, so contributions are welcome, and I want to thank all the persons that have contributed so far to the library. That's all. See you next time.